So next, let's talk about these tilt shift Java, CPP, and neon functions. As you might notice, they're called on the Speedy Tilt Shift class. The class directly and not the object, so that means these are static functions, which means you don't have to worry about the instance that you're calling it on. Instead, you're calling it on the class itself, and so if you open up the Speedy Tilt Shift.java class, you'll be able to see these functions written out. The Tilt Shift Java, and you'll see CPP and neon below it. And you'll notice that each of these functions takes in a bitmap of input. That's your input image. It'll take in your sigma values, it'll take your A row values, and it'll use those to produce the output bitmap, which it will return. And so these have already been set up for you as functions inside of the Speedy Tilt Shift.java file, but you're going to be replacing the manipulation of the pixel values in order to produce that output bitmap. To do that, you might want to understand a little bit about what bitmaps really are and what these input and output bitmaps are in this Android code as well. And so I'll give you a little bit of an explanation here of what a bitmap really is. What you should think of as a bitmap is a set of pixels that are in a grid array, which is how standard pixels usually are, right? That's how we usually think about images, is that an image is made up of a grid of these pixels. And there's going to be many more pixels than what I've drawn in this grid here. But this pixel has some color value. This pixel has some color value. This pixel has some color value, and so on and so forth. And so as these pixels have different colors, that's what's going to generate for you a pleasing image that you'll look at. If you look at what it means to be a pixel and to have a color, though, each of these pixels maps out to being actually composed of, in this case, 32 bits of data, right? And what we saw, or what we would see if we look at this format, it says that we're doing things in the format of ARGB8888 for our output bitmap. And our input bitmap also has that configuration, which we set up somewhere else in the code. But if it has ARGB8888, that means it has 8 bits to represent its alpha value, 8 bits to represent its red value, 8 bits to represent its green value, and 8 bits to represent its blue value. If we're saying that this is the least significant bit over here and the most significant bit over here, then these 32 bits represent the color value of this pixel. Which is to say that if you got 8 bits over here for this blue part, right? And all of these are 1, then that means it's very, very blue, right? Because that number of 1111111 corresponds to 255, and that's the maximum value that you could represent with 8 bits, and so that's going to be very, very, very blue. If, on the other hand, these are all zeros, then it would be not, that pixel value would be not blue at all. Your display would not emanate any blue light to represent that pixel. And so you may have some values that are in between that. In fact, there are 2 to the 8 different combinations of 1s and 0s that you could throw in to represent how blue you want that pixel to be. Similarly, you could have 8 bits to represent how green that pixel is, and 8 bits to represent how red that pixel is. And then there's this A value. A is the alpha channel, and so it's how transparent you want that pixel to be or not. Since there's no other overlays that you're placing on this, it doesn't really matter what you make A, so we should just set them all to 1. Which in hex, by the way, is OXFF. Sorry, my pen is acting up here. F as a hex digit corresponds to 1111 in binary. So if you put 2 of them next to each other, it's 1111, 1111. However, if we wanted to get what is the blue value of this pixel, you can take what you're given, I guess I should say, is that the pixel value, you get all 32 bits at once. So you get this whole 32 bits of whatever, how blue it is, how green it is, how red it is, how alpha it is, all in a row. There's no, you get it all at once. So if you wanted to take that pixel value and then you wanted to extract, well, I only care about what the blue is in this channel, then you could mask it by saying, I only want to look at these bits by taking this value, which we could call P. If we say this whole thing is P, then we'd say P ANDed with OXFF is going to generate the blueness. Alternatively, we could say P blue is equal to P mod OX100. Those do the same thing. I'll leave it as an exercise to the reader, to you all, to figure out why those are the same thing. But arithmetically, they actually work out to mask. All of the other pixels will go away and it won't care about those anymore. But instead, it will only care about those 8 least significant bits and preserve those, and then you'll be able to see what the blueness is, right? So if you don't understand this, I recommend you work out the arithmetic and understand why the arithmetic works a little bit. Sit down and take a look at it. It's a worthwhile thing to understand how that kind of masking does work. If you still have questions, of course, ask on Slack. So then how do we get the green value? Well, you can do, what you will need to do is you'll say, well, I care about these next 8 bits, not the first 8 bits, but the second 8 bits. So what you can do is you can shift your pixel value by 8, and you'll do it like that, which basically moves your pixel array so that these green values are now in the least significant slots. And what you'll want to do is take that, and now you'll AND this with OXFF, and that will produce for you the green value that you want. And just as before, you could also equivalently do mod OX100, hex 100, and that would also get you the value that you want for green. And similarly for red, we can shift by not 0, not 8, but now 16 bits over, and AND that with OXFF, and that will give you your red pixel that we care about. And that's how you can extract your red, green, and blue pixels. If you want to put those pixels back and you have these red, green, and blue values, what you can do is you can say, well, however blue it is, I want to add that to the mix. So we can say P equals P blue plus, now I want to add the green pixels to the mix. But if I just add P blue and P green like this, that's going to mess them up because blue and green will overlap with each other. So let's move green so that it's on its own slot. And the way you can do that is to left shift it by 8, which moves the green ones so that they're in their own indices of the array, of bits here, if you want to think of it this way. And then similarly for red, we'll shift that one by 16 now to the left. And we'll use our OXFF and shift that by 24. That's what the shifting operator, if you don't know what that is, you can look that up as well. Or you could ask your teammates to help explain that to you. Or you could ask me in office hours or in class, and I'll go into more detail as needed. But that's how you can go back and forth from starting with your pixel value. You can get your blue, green, red, and alpha components. And then from your those components, you can also go to your pixel value. And so now each of these pixels is inside of this array. And these are stored in what's called a raster scan order, which means this is the 0th entry, this pixel is the 1st entry, this is the 2nd entry, the 3rd entry, the 4th entry, the 5th entry, 6, 7, 8, and in this case 9, because there's 10 pixels wide on this image. And then the 10th pixel is over here, 11, 12, 13, 14, 15, 16, 17, 18, and 19, and so on and so forth. But that's called raster scan order, left to right, top to bottom, just like you would read a book in English. So what do we mean here? Well, that means that if you've got a bitmap image, then if you've got a bitmap image and each pixel is represented by these 32 bits, you've got 32 bits here, 32 bits here, 32 bits here, 32 bits here, and so on and so forth for each of the pixels, and that together will generate your image. So how does this look in code? Well, if you look at this tilt shift Java function, you see int array of pixels, and we have an integer array that we are actually allocating first, that has how many entries of it? Well, height times width, because that's how many pixels there would be in an image. And we can get the pixels from the image by calling input, which is this input bitmap, .get pixels, and that's going to store into this pixels array all of those pixels of your bitmap into this integer array. Now, an integer array, happily, has 32 bits per integer. And so every index of this array contains those 32 bits that we just said talk about the alpha, red, green, and blue values of each pixel. So we can access a pixel using the array accessing methods by giving this a different index, pixels I here. And then we can manipulate it by doing what we said before of either modding by OX100 or ANDing with OXFF, and bit shifting as needed to get to your different channels of, for example, green or red. And the same is true of your output bitmap, right? So we've got our output bitmap. We generated it at the first line here. Based on their input width, input height, we allocated it. And with a configuration that we want to format it with this nice ARGB 8888, which again lets us use 32-bit integers to represent pixel values. So we generate an array for your input pixels. We generate an array for your output pixels. We get the pixels for your input and from your input and store them into that pixels array, manipulate them, and then we set the pixels of the output bitmap to be of the pixels out array. So now let's talk about the manipulate part that I kind of just skipped over really quickly there. Inside of this manipulation, what you're going to want to do is iterate through each pixel value. So for example, I equals 0, and I goes from 0 to input.getWidth times input.getHeight, which will iterate through every single value inside of this pixels array. And we use I++ to go from one pixel to the next. We can get our different pixel values, B, G, R, and A. And just temporarily here, what we're going to do is we're going to set G equals 0 to set all green values to 0, just to demonstrate that we're doing something here. Then we're going to set our color by taking these B, G, R, and A and put them in the right places. So again, you want to bit shift your alpha value by 24, your red value by 16, your green value by 8, and then your B value as is. And you see we're using OR here, but plus also works just the same way with unsigned integers. So this combines these different pixel values, pixel value components together to create a pixel value, and then a pixel value gets stored in the output array, and that array gets written to your bitmap. It may be complicated as a process to understand, so I think dwell on it a little bit and you'll understand. Now, this is a per pixel operation that we're doing. So we're iterating on every pixel. we are setting its value somehow to 0 for G, and then we're putting its color together and writing it as an output. In reality, what you're going to be doing with your tilt shift operation is iterating not only on every pixel, but once you iterate on each pixel, you'll also want to iterate on a patch of pixels around that pixel so that you can perform the Gaussian blur operation. And we can talk about that Gaussian blur operation if you'd like in more detail if I see enough interest in doing that over Slack. So this is the Java code. We also have code on the C++ side that's set up as a template for you to work from. So just like with the Java code, we're also going to be dealing with bitmaps. Just as with the Java code, we'll be dealing with this ARGB 8888 representation. So just as the Java code, it'll be 32-bit integers for each of the pixel values, of which there are height times width. And there's an input array, there's an output array. You can get the pixels from the input array from your bitmap, and you can set the pixels of your output bitmap from your output array. But what's different here is what we're doing in between for the manipulation. For the manipulation, we're calling this tilt shift CPP native. And so you'll see this is italicized, which helps you see that it is a native function by the IDE here, the integrated development environment, that is, of Android Studio. And what that means is that it's being called from your native library. Your native library you'll set up, it's already been set up for you, using this syntax here of loading the native lib library on application startup. And so that code is written in nativelib.cpp inside of the CPP folder, and you can see what it looks like here. This is the tilt shift native CPP native function call. You saw that it started out compressed, and when I double clicked on it, it opened up to what it actually looks like. I accidentally clicked on something and it took me to where we're setting it up as a function prototype in the Java code. You will have to do that if you wanted to create more native functions. Public static native int, and then the name of it. Then if you click on the C++, it'll take you to C++. I actually didn't know that functionality existed, but I just discovered it literally 10 seconds ago now. Okay, so anyway, you'll see that it has this really long moniker, this really long name for the function, but that's necessary because this goes through the package, and then the class, and then the actual name of the function, and that's how it stitches it together. It has all of the same arguments, the same parameters that you set up in the Java side of things, except it also has an additional JNI environment parameter, JNI environment. It's a Java native interface environment. So that Java native interface environment is necessary in all these calls, and then you need to actually use it if you're going to access an object or if you're going to access an array. And in this case, we're accessing arrays. So you'll see that you've got this jint star pixels, which is getting access to these array elements, array elements of the input pixels and for the output pixels as well, which is going to let us get and set the pixel values appropriately. So yeah, you've got access to these arrays. Now we can manipulate those pixels in the input and output pixel arrays. And guess what? The arithmetic is the same. The math here is fundamental, it doesn't change, and so you can do the same thing that you did with the Java code, except in C++. And what we're doing in this code, instead of setting green to 0, we've set blue to 0. And so you should see a different result when you're playing around with this on the sample application. Now, of course, instead of just green and blue setting to 0, you'll be actually doing the Gaussian blur, and then you'll be doing the identical Gaussian blur between the Java and the native execution. So you shouldn't be able to tell a difference, assuming that your code works properly. You'll see that you need to release your integer array elements here at the end of this, and then that will let you do what you need to do. And then finally, one last thing is that there is this neon native function, and that's also going to be implemented by you, but we'll talk about how neon works at a later lecture. So just hang tight, and we'll show you how to use the neon vector computing library extensions. So that should give you a basic introduction to the template that we have for this application, and so you can use that to construct your assignment. Okay, that's all. See ya.